Hello, Ross. Let's take a look at rates of change of trig functions from 4.8. We're going to take a look at the cosine curve and the tangent curve. We're asked to use intervals to calculate an estimate for the smallest rate of change. I guess it should be instantaneous rate of change. Instantaneous rate of change. So I'm going to use sketches to help me predict where my rate of change should be the smallest. I want to make sure I understand that any negative rate of change is going to be smaller than 0, like I have rates of change of 0 for the cosine curve at 2 pi n. But, I mean, that could be a pretty quick question. When are the rates of change 0? At 0, at 2 pi, at 4 pi. Now, we want to figure out when the rates of change are smaller than 0. So it looks like on the cosine curve, it's going to happen at pi by 2. So I'm going to try to calculate an estimate for the instantaneous rate of change at pi by 2. That's pi by 2, by the way, because my full period is 2 pi. And that means that my quarter period is going to be pi by 2. So let's see. If I want to use following intervals, then I get to recycle the fact that I know that pi by 2 comma 0 is on my curve. It might take a little bit longer to converge than centered intervals, but I know I can just start smaller then. Next problem, zoom in real close here. Assuming that I'm going to use a following interval, I'm more used to finding instantaneous rates of change at like integer inputs. So if you ask me for the rate of change at 3, I could go from 3 to 3.1 and 3 to 3.01 and 3 to 3.001. Just adding 1/10, 1/100th, 1/1000th is pretty easy to do on 3. To get a number a little bit bigger than pi by 2, I don't want to try doing like pi 0.1 divided by 2. I don't want to try to, I guess I could do like pi divided by 1.9, and that would be a little bit bigger. Now, my advice is do what you were doing with integers. Just don't try to simplify it. Like, let's find the average rate of change from pi by 2 to, let's go 1/100th larger than pi by 2. Well, what's 1/100th larger than pi by 2? How about pi by 2 plus 1/100th? Let's make sure we announce to our reader that we're doing an average rate of change. Let's tell our reader over which interval we're doing our average rate of change. I'm going to substitute into my formula here, I suppose. This is going to be the cosine of pi by 2 plus 0.01. Technically, this is the cosine of pi by 2, but let's keep in mind that we already know what that number is. And my denominator, I guess I could do pi by 2 plus 0.01 minus pi by 2, but I already decided that I wanted delta x, or delta theta in this case, to be 0.01. So yeah, next time through, or maybe even right here, let me just lightly cross this out and say, well, it's just going to be 0. So maybe I don't even need to type in minus 0, do I? Let's try in radian mode. We'll talk about what happens in degree mode in a sec here. Cosine of bracket pi by 2 plus 0.01, error. Cosine of pi by 2 plus 0.01, and divide that by 0.01. And we get about negative 0.999983. If we've seen the rate of change of the sine curve already, then maybe we're not surprised what this number is pretty close to. Still, we haven't shown convergence, so let's make this interval much smaller. Let's go from pi by 2 to pi by 2 plus 0.001. And this time, I will show my calculation. You don't have to, but I'm just going to type in plus 0.001. Let's not forget there is a minus 0 here, divided by 0.001. This should be pretty fast to get into my calculator. Cosine of pi divided by 2 plus 0.001 divided by 0.001 is about negative 0.999999. 1, 2, 3, 4, 5, 6. Yeah, root 3. And that's evidence to the nearest unit, to the nearest tenth, to the nearest hundredth, to the nearest thousandth, to the nearest 10,000th, even, well, yeah, nearest 10,000th, that my rate of change is converging towards -1. Instantaneous rate of change at pi by 2 is going to be -1, or I'm estimating it's -1. Okay. Note the units. Pi by 2 is unitless. My angles are unitless. That means that this 0.01 is also unitless. So I have unitless ratios divided by unitless ratios, giving me a unitless ratio. Unitless. It's actually just like a slope, a ratio of rise to run. And here's the other problem with degree mode. If we tried, you might think degree mode would be easier to get like centered on following intervals close to 90. Let me try doing the average rate of change from 90 degrees to 90.01 degrees, I guess. That's going to be the cosine of 90.01 degrees, and my calculator can do that if I'm in degree mode. Minus 0 all over. My delta theta here is going to be 0.01 degrees. All right. Into degree mode, please. The cosine of 90.01 degrees is going to be a number very close to 0, a little bit lower than 0. I forgot to point that out. And then I subtract 0 from that. And then I divide it by 0.01 degrees. And I get a number first off that doesn't look familiar to the numbers from before. These numbers, it looked pretty easy to predict where we were converging. Versus here, this looks like some weird irrational number. This is more ammunition in the fight of radian mode versus degree mode, where people say, oh, I don't like radian mode because there's these irrational numbers in it. Well, the rates of change are going to be rational numbers. You say, oh, this is easier because these numbers are rational, but the rate of change isn't rational. Here's the bigger issue, though. The units on this rate of change are the cosine of 90.01 degrees is a unitless ratio, but the units on my denominator are degrees, and that means that this rate of change is in per degree, which is a really awkward unit. If I were to try to calculate over a smaller interval, cosine of 90 point, let's make it much smaller, 1, 2, 3, 4, 5, 6, 1 equals divided by 0.1, 2, 3, 4, 5, 6, 1. I forget. And that's from 90 degrees to 90.1234561 degrees. I get about -0.01745-ish. So yeah, I could approximate that my instantaneous rate of change is converging to this number, -0.01745, but what's the significance of that number? And its units are goofy too, so radian mode's the way to go if you're doing rates of change. You're going to have to in calculus. Let's go back to radian mode and take a look at the tangent curve. There's 2 cycles from 0 to 2 pi. Notice here that your tangent curve is never decreasing. Its rates of change are always going to be positive when they exist. And sorry, I've done a terrible job of my sketch here because this should be symmetric in between there. That's at pi, right? We could calculate for the smallest rate of change. I'm going to predict that it's going to happen at 0 or pi or 2 pi. And we could calculate it around 0. Let's calculate it around pi, just because it makes the calculations a little bit more interesting. Why don't we try a centered interval here as well? So we're going to lose the advantage of being able to recycle the value, but let's just see what happens. Average rate of change from, I'm going to need a number a little bit smaller than pi. Let's go pi minus 0.1. And a number a little bit bigger than pi. Let's go pi plus 0.1. So I go 1/10 to the left and 1/10 to the right, like I usually do for a centered interval. This is going to be the tangent of pi plus 0.1 minus the tangent of pi minus 0.1 all over. Just be careful with your denominator here. The safest but longest approach might be to do pi plus 0.1 minus pi minus 0.1. Notice pi minus pi eliminates, and then you get 0.1 minus negative 0.1. Definitely not 0. Our denominator is going to be 0.2. We sort of decided that when we decided we were going to use a centered interval of size 0.1 to both sides. We decided that we're doing a centered interval of width 0.2. There. Okay, I don't want to approximate in the numerator. Let's make sure we understand there's no tan pi minus tan pi eliminating here. The tangent ratio isn't distributive either. I'm not doing anything in my numerator here. I think the next time I'm just going to write this down. Okay, calculator. What is... I can hit equals in my numerator and divide by that denominator. Let's go tangent of pi plus 0.1. I'm in degree mode. Back to radian mode because I'm in grade 12. Tangent of pi plus 0.1, close that bracket, minus tangent of pi minus 0.1. Okay. Do not approximate pi to 3.14. It's not going to be precise enough for us, especially if we start subtracting 1/100th or 1/1000th from 3.14. It's just, we're going to be way off. Equals divided by 0.2. I get about 1.00335-ish kind of thing. Again, a unitless ratio. Unitless ratio divided by unitless ratio is a unitless ratio. Now let's make the interval much smaller, 0.01 to pi plus 0.01. And I think I'm just going to go to calculator town on this one. Let's do, reading in here, inserting zeros there and inserting zeros there. Let's do, I'll try it as one go. Bracket, tan, bracket, pi plus 0.01. First bracket closed, minus tangent of, next bracket, pi, minus 0.01. Close bracket, close my bracket on my numerator, divided by 0.02. Yay. 1, 2, 3, 4, 3, 3, 3. To the nearest unit, to the nearest tenth, to the nearest hundredth, we have evidence that the instantaneous rate of change at pi for the tangent curve is about 1. And it's no coincidence that it's the same, or it's the opposite of the smallest rate of change of the cosine curve. This nice number, this rate of change of 1, again, will only show up in radian mode. If you calculate your rate of change in degree mode, you're actually seeing the convergence from degrees to radians, but it's very hard to see because those irrational numbers, it's hard to see what they converge to. So, use your sketches. If you use your sketch, label your sketch. Do this as one expression. Try this trick of just saying what you're doing and let the calculator do it so that you're not approximating. Approximating too soon is usually where most of the problems come from here. Okay, try it out.